Hello, everyone, and welcome to week number 4 of the fourth quarter of Introduction to Statistics. This week, our topic is on the tests about the mean. Specifically, we will be presenting the 3 different t-tests and the analysis of variance. To clarify our intention for this lesson, let us take a look at our lesson objectives. Here are the skills that you are expected to develop by the end of this week. Number 1, everybody should be able to determine if the conditions for testing hypotheses about population means are met by the sample data. Second, you should also be able to determine the appropriate test about means. Number 3, you should be able to use the appropriate t-test to test hypotheses about the population mean or to compare 2 different means of 2 different groups of individuals. Number 3 is to perform and interpret the results of analysis of variance or ANOVA using statistical software. All right, now before we present the 4 different statistical tests that are covered in this lesson, I would like us to take a look back at some of the important concepts that we covered in the first 2 weeks of the quarter. Here are the things that we are hoping that you should already know so far in the process of hypothesis testing. Now, you would remember that at the beginning of the quarter, the very first thing that we presented or we talked about is the concept of hypothesis as it applies in statistics. We said that in the context of statistics, hypothesis takes a very defined definition in comparison to the more general definition of how it is used in the sciences. So in statistics, we say that a testable statement on the basis of an observed data about a random variable is what we call as a statistical hypothesis. And the process that we are interested in is testing that hypothesis by gathering data from a certain sample that represents a population and trying to determine whether or not we're able to gather enough evidence to reject a null hypothesis. So in a nutshell, we say that hypothesis testing is a systematic process of determining whether there is enough statistical evidence to support a hypothesis by rejecting another hypothesis. You would remember that in the previous discussions, we presented the 5 different steps in hypothesis testing. But for this lesson, we decided to present another version of that process by looking at the hypothesis testing process as composed of 6 different steps. So step number 1 of the hypothesis testing process is stating the null and the alternative hypotheses. So whenever there's something that we would like to test, we usually indicate or we usually determine what you call as the null and the alternative hypothesis. Statistical evidence is tested to determine whether or not the null hypothesis can be rejected so that we can provide support for the alternative hypothesis. Remember that the null hypothesis is the one that is being considered in hypothesis testing, whether or not there is enough evidence to reject or not reject the null hypothesis. Now, in this process, eventually what we want to do is to be able to come up with a decision whether, as we said, we will be rejecting or not rejecting the null hypothesis. As we make this decision, we have to be very careful because we can commit 2 different errors in hypothesis testing. And we said that whenever we reject a true null hypothesis, we are committing a type 1 error. And failing to reject a false null hypothesis is considered to be a type 2 error. Now, rejecting a true null hypothesis or a type 1 error is determined based on what we call as the significance level or the alpha value. This is something that is determined by the researcher to be the acceptable probability of committing a type 1 error. So that becomes our second step in the hypothesis testing process. The third step is to determine the appropriate statistical test and to determine the test statistic. So to clarify, because this is actually the part of the hypothesis testing process that we did not talk about in detail, an important part of the process is to choose the appropriate statistical test depending on the context of the problem, depending on the kind of data that we are working with, and depending on the intention of the statistician or the researcher. So there are two different kinds of statistical tests. We have what we call as parametric tests and non-parametric tests. What makes them different from each other is that parametric tests are based on the concept of the normal distribution. So these are tests that always assume that the data that we are working with is normally distributed. And because of this assumption, there are certain conditions that are need to be met by the data in order to use or employ these parametric tests. If a certain data set or if the sample data does not satisfy any of these conditions, then every parametric test has a corresponding alternative, which we call as non-parametric tests. These are tests that have lesser conditions, but the compromise is that they are considered to be less powerful than the parametric counterparts. We also said that tests can be further classified, or every test can further be determined as either one-tailed or two-tailed. Whenever the alternative hypothesis talks about an inequality, whether one mean is greater than the other or one mean is less than the other, then we say that the type of test that we need to employ is a one-tailed or a directed test. On the other hand, if the alternative hypothesis is interested or it states that there is a significant difference between two different means or two different parameters, that we say that the test that is appropriate is a two-tailed test. Now, once we have identified the appropriate statistical test, we're able to compute for what we call as the test statistic. So the test statistic is actually the result of the statistical test. I will be showing you some examples later so that you can better understand how the test statistic is computed based on the appropriate test that we determine. The next step is to determine the rejection region if ever we are working with the traditional method for hypothesis testing, or using the p-value if we're using the p-value method. This is a determined standard to compare with the test statistic or the value of alpha. So if we're working with the p-value method, or if we're doing the hypothesis testing process through the p-value method, we usually compute for the p-value, not only the test statistic. And once this p-value is computed, we compare it with the significance level or alpha, and then eventually be able to determine an appropriate decision. So the decision again is whether to reject or not reject the null hypothesis based on the decision rule that is determined in the previous step. And finally, once a decision has been made, we go back to the context of the problem. We introduce the random variable that we are interested in so that we can come up with a conclusion. So this is responding to the underlying research question based on the decision of rejecting or not rejecting the null hypothesis. Now, before we proceed with examples of the different tests that are covered in this lesson, it is necessary that we understand in general what exactly it means to test a hypothesis about the mean. Field in 2009 said that researchers are sometimes interested in looking at differences between groups of people. In particular, for example, if you are working with an experiment or you're doing an experimental research, you may be interested in manipulating a certain variable and try to see what happens to people or individuals in general so that we can make causal inferences. For example, you may be interested in determining whether or not a certain study practice is going to be effective for a certain group of students. So you measure their performance before they do or they implement the study method. And then you give a similar test at the end of their exposure to the study method and try to compare whether or not the mean from before the intervention and then after the intervention are significantly different from each other. So whenever we are interested in these kinds of comparisons, then we should be able to employ a test about means. In some other examples, you may take a look at a specific sample from a certain population and then let's say you want to determine whether or not the mean from your sample is statistically significantly different from what is known about the population. For example, if we know that the mean height of Filipino teenagers is hypothetically, for example, around 60 inches, and then you gather a group of basketball players, and then you identify their sample mean to be around 70 inches, then one of the things that you can do with testing a hypothesis about the mean is to determine whether or not the 70 inches and the 60 inches are significantly different from each other. And these are the kind of problems that we are going to be discussing in this lesson. Another example that field provides is, for example, if we take two groups of people and randomly assign one group a program of dieting pills, and then let's say another group, which will be considered as the placebo group or the control group, and this group are given sugar pills instead of the dieting pills. And then after a certain period of time that they take the pills that were assigned to them, we measure their weight. Then we can compare the weight of the individuals before the program and then after the program, and then try to see whether or not there is in fact a significant difference between the two different groups. So that's another kind of problem that we can work with by looking at the different tests that we will be discussing in this lesson. So the first test that is a part of this discussion is the one sample t-test. The one sample t-test is used in testing a population or hypothesized mean versus the sample mean when the population variance is unknown. On the other hand, if you want to test whether two dependent or paired sample means are significantly different or not, then the appropriate test is the dependent t-test. I will discuss later what we mean by dependent or paired sample means. The third one is what we call as the independent t-test. And this is when we want to test two independent sample means from the same population when the population variance is unknown. And finally, after these three different t-tests, we will also introduce the concept of the analysis of variance, wherein we take a look at testing three or more means that are considered to be, whether or not those three different means are the same. Now, I mentioned a while ago that when we determine the appropriate statistical test, we have to be familiar with the different assumptions and conditions that would allow us to use those specific tests. So for testing hypotheses about the population, here are 5 of the more common assumptions and conditions that we need to check in order to use the t-test and the ANOVA. The t-test is a parametric test. It is a test based on the normal distribution. Therefore, using it requires that several conditions are met by the distribution. So these are the 5 different conditions that we will be checking in order to determine if the t-test is an appropriate test. So the first condition is what we call as the homogeneity of variance. Because they are used to test different groups of people, the independent t-test requires that the standard deviations of the groups are roughly equal. In some other textbooks, they make use of the terms homozygosity and heterozygosity, which means that whenever we want to employ the t-test for independent samples, we want to make sure that the variance or the standard deviation of one group is not significantly from the variance or the standard deviation of the other group. In fact, we can employ a hypothesis test to actually check for this assumption. So you can think of it as a hypothesis test within a hypothesis test. And that's actually very common. Now, in this lesson, since we will not be discussing how you're going to employ that specific test to determine if the condition of homogeneity of variance is met by the data, we will just assume that in all of the examples that we will be working with, that this condition is actually satisfied. The second assumption or condition is the normality. So the sample distribution is normally distributed. Actually, when we say normality, what we want in t-test is to assume that the population from where the sample data was taken from is normally distributed. But because we usually do not have information on whether or not the population is normally distributed, we will rely on the characteristics of the sample data in order to inform whether or not the population is somehow normal. Remember that the data that we get from the sample should be representative of the data that we should get from the population, especially if the sample that we have obtained is representative. So if the sample is normally distributed, then more likely the population distribution should also be normally distributed. The third condition that we need to meet is the condition of randomization. We say that for parametric tests, the sample should be randomly chosen. This is a condition that would be very easy to check. And then number four is that the data that we are interested in, or the random variable that we would like to test, is measured at least the interval level. So it's either interval level data or ratio level data. And finally, the last condition is independence. For the one sample t-test and the independent t-test, data from one individual must be independent from the data of another individual. So that means that the information that we get from one individual in the sample must not be in any way related to the data that we get from another individual in the same sample. All right. Just a disclaimer, the scope of this course does not include testing distributions for these conditions. Hence, for all of the examples, we shall assume that some of these conditions are already satisfied unless there is a way for us to check whether or not some of these conditions are met by the data. For example, yung randomization and the measurement scale are easy to check. So we should be able to evaluate whether the data meets these two different conditions. On the other hand, the other conditions we will assume, therefore we will call them as assumptions. Okay, so I think we are now ready to discuss the first test, which is the one sample t-test for them. Now, this test is used to test whether the mean of a population is equal to the mean of a sample of the same population when the population standard deviation is unknown. It is based on the t-distribution that is used to calculate critical values for the test, and the t-test assumes that the population variance is unknown. Okay, so the population variance must be unknown. We've already presented the concept of the t-distribution in one of the lessons that we talked about in the third quarter. But just to remind you, the t-distribution is used whenever we are working with a sample size that is usually less than 30. This is a distribution that is similar to the normal distribution. So if you remember the different characteristics of the normal distribution, some of these characteristics are also eminent in the t-distribution. What are these characteristics? The t-distribution is also bell-shaped. It is symmetric about the mean, and it is asymptotic to the x-axis. On the other hand, some of the characteristics of the normal distribution are not the same for the t-distribution, and these are the following. The standard deviation is greater than 1. Although it is also a family of curves, the family of curves is based on degrees of freedom. And as the sample size increases, the t-distribution approaches the normal distribution. All right, so let's take a look at an example of the one sample t-test. Now remember that the intention or the objective of a one sample t-test is to compare the mean from a sample data with a hypothesized mean or the mean of the population. For example, if a certain automobile manufacturer advertises that its new hybrid car has a mean gas mileage of 50 miles per gallon, and we take a random sample of 35 hybrid vehicles and test their gas mileage, we can test whether or not the advertised mean gas mileage is in fact true at alpha is equal to 0.05. So the 50 miles per gallon in the problem is what we call as a hypothesized mean because it is claimed to be the mean of all of the cars produced by the automobile manufacturer. Now, the sample data that we see over here on the right should be able to generate a sample mean. And what we're going to do is to test whether or not the sample mean is in fact significantly different or not significantly different from what is claimed by the automobile manufacturer. Obviously, if it turns out that the sample data or the mean of the sample data is not significantly different, then that is enough evidence to say that the automobile manufacturer is correct in its claim of a gas mileage of 50 miles per gallon. But if we're able to reject the null hypothesis, meaning there is enough evidence to say that the sample mean from this data is statistically different from the 50 miles per gallon, then that should dispute the claim of the manufacturer. So let us follow these steps in hypothesis testing, beginning with step number 1, which is to identify the null and the alternative hypotheses. So the underlying research question, if you think about the problem, is that it's asking us whether or not there is a significant difference between the sample mean of the 35 hybrid vehicles and the hypothesized mean provided by the manufacturer. So to answer that question, the null hypothesis would say that there is no significant difference between these two different means. Therefore, the sample mean or the mean from the sample is equal to 50 miles per gallon. On the other hand, the alternative hypothesis would contradict that, and it would say that there is a significant difference between those two different means. So if there is a significant difference, then they should not be equal. Step number 2 of the hypothesis testing process is to set the value of alpha. So we set the alpha at 0.05 as requested in the problem. Now, before we proceed to testing before we employ the one sample t-test and determine the test statistic, it is important that we try to determine first whether or not the one sample t-test is appropriate, and if it is appropriate, whether or not the conditions that we have determined are met by the data. So the first question that we need to answer before we proceed is if we are interested in testing if the mean of a population is equal to the mean of a sample, and if the standard deviation of the population is unknown. So these are things that we talked about as characteristics of the one sample t-test. And if you think about it, the answer to these questions is yes. We're interested in comparing the sample mean with a hypothesized mean, and the standard deviation of the population is not given in the problem. All right. Now that we have determined that the t-test is appropriate, we need to look at each of the 5 conditions and try to see if all of these are either assumed or satisfied. So for the homogeneity of variance, we shall assume that this is met by the data. For normality, one of the things that we can do is to create a histogram for the sample data. And this is exactly what we see here on the left side of the screen. And we should be able to notice that the histogram appears to be normally distributed. So we can say that the condition for normality is met by the data. But we take note, however, that depending on the histogram to determine whether or not the data is normal is quite subjective, because one person can look at the same histogram and say it's normally distributed, while another person would say that it is not normally distributed. So usually we employ another kind of hypothesis test in order to determine whether or not a certain sample data is normally distributed. In this lesson, we will not be introducing that hypothesis test for normality. However, in the next lesson, in our next week's discussion, we will be presenting what we call as the Kolmogorov-Smirnov coefficient to determine whether or not a data is normally distributed. All right. The third condition is that the data is based on a random sample. And this is quite obvious from how the problem is stated. The sample was randomly chosen. The measurement scale is in the ratio level. Since gas mileage is a ratio level data, then the measurement scale condition is also satisfied. And finally, since the mileage of a hybrid car is not affected by that of another hybrid car, then we say that the condition for independence is also met. All right. Now, for all of the examples that we will be presenting, we will be using a set of calculators that are made available by Social Science Statistics. I have already uploaded the links to these calculators to K-Hub. But should you want to an access to these calculators, you should be able to see the link on the bottom of your screen. Now, if you click the calculators tab here, it should give you the list of all of the available calculators that the website provides. For this example, we will be using the single sample t-test calculator. So what we're going to do is to indicate the population mean, and then we will have to copy and paste the samples. We will have to copy and paste the samples into this part of the website, and then identify the significance level, which we already know is at 0.05. And since the alternative hypothesis is states that there is a significant difference, or the sample mean and the population mean are not equal, then that has already been encoded. Then we can press calculate, and we should be able to find that the calculator would generate the result. All right. Now, I'm not going to do that here, but we should be able to find the results in the next slide. So if you do the test on your own, you should be able to find that the t-value is negative 3.30, and the p-value is 0.002. All right. So we take note that the t-value, sometimes we also call this as the computed value, is what we call as the test statistic. So whenever you are asked what the test statistic is, this is basically this value over here, which is actually a score in the t distribution. On the other hand, the p-value, which we will be using to compare with the alpha value in order to determine the decision rule, is the one that we see over here. Okay, so let's proceed with step number 4, where we determine the decision rule. At alpha is equal to 0.05 with a two-tailed test, we remember that visually what we mean by alpha at 0.05 is that the two different tails of the normal distribution would share 5%, an area of 5% in the curve bounded by, in the area bounded by the normal curve. All right, so the decision rule is that we will reject the null hypothesis if the p-value is less than 0.05. Now that we have determined the rule to decide, we can now decide what we will do with the null hypothesis, whether or not we will reject or not reject the null hypothesis. And we say that since p is less than 0.05, p specifically is 0.002, and that's less than 0.05, then there is enough evidence to reject the null hypothesis. And the result is significant at alpha equals 0.05. Finally, the last item or the last step in the hypothesis testing process is to write the conclusion. And we're going to do that by following the APA 7th edition format, where we identify or we disclose the alpha value, the mean and the standard deviation of the sample data, as well as these other values. So let's take a look at what these values are. M represents the sample mean, and then ST represents the sample standard deviation. So once the sample is presented in the conclusion, we should be able to enclose in parentheses these values so that anyone who looks at the report would be able to have access to this information. Aside from that, we should also be able to present what kind of distribution the test is based on. So because we use a t-test, the distribution is a t distribution. And the degree of freedom is also given. So 34 is determined by subtracting 1 from the sample size. So because we have a one sample t-test, then the degree of freedom would be n minus 1. So that gives us 34. This is not always the case for all of the t-tests. And you would discover later that sometimes we subtract 2. And the subtrahend actually depends on the number of independent groups that we are working with. The negative 3.30 here is the test statistic, and the p-value is the one that we computed based on the test statistic, which is 0.00. So the conclusion for this specific problem is at alpha equals 0.05, the mean gas mileage of a sample of hybrid car was found to be significantly different from its manufacturer's claim of 50 miles per gallon. So what we're saying now here is the mean of 48.6 from the sample data is statistically significantly different from what the manufacturer is claiming to be 50 miles per gallon. All right, so we will end the lecture here, and we will continue with the next part of the lesson.